So today's speaker is Olga Aryasova with the talk Homogenization of multivariate diffusion with semi-permeable reflecting interfaces. Please.
Today I present my joint work with Ilya Pavlukevich, Uni Jena, and Andrei Pilipenko, Institute of Mathematics, Kiev. Oh, and how can I, just a moment, I failed to change the slide. Okay, I don't know how to change it. Full screen regime. So, mathematical homogenization problem usually deals with the study of effective parameters of a system, which coefficient, which parameters varying very fast. For example, let us consider this partial differential equation, where A is a thermal conductivity tensor, and suppose that this tensor A has a periodic structure. It is a periodic, and alpha be very small, epsilon be very small. And we are interested in some effective thermal conductivity of this system if epsilon tends to 0. As a result, we obtained a new temperature distribution U, which is the limit of U epsilon as epsilon tends to 0, and U will be a solution of new homogenized equation with constant parameter A. The same problem can be considered in stochastic dynamics. For example, we can consider stochastic differential equations, the coefficient of which are also periodic smooth function. And again, if epsilon tends to 0, we obtain some effective drift and diffusion coefficient A and sigma. So, generally speaking, the homogenization problem consists in determining this effective characteristic of some equation. There are a lot of literature, both in deterministic and stochastic approaches, but I intend to speak today about a little bit different problem. Namely, let us consider diffusion with a narrow locating semi-permeable barrier, like interfaces like the hyperplane. This model reminds foil composite materials, which consist in some media, some material, for example, glass wool, which are reinforced by aluminum foil, for example. If the layers are very thin, we can be interested for the some effective conductivity of this material. And there are a lot of papers in chemistry, biology, physics, and etc., which has such a kind of problem.
Excuse me, can I ask a question? Can you please go back to the previous slide?
Yeah.
And the slide and one more. Okay. So usually in these problems, we suppose that matrix A is periodic with respect to spatial variable X in all directions. Yeah.
Yes.
So as far as I understand, you want to consider the case when it is periodic only in one direction, for example. Yeah.
Yes.
In one coordinate.
Yes, in one coordinate, namely, yeah.
Oh, okay, something.
So it will be some multivariant invariant problem. And let me just formulate it in mathematical terms. Yeah.
Mhm.
So we are given by m-dimensional Brownian motion, and epsilon will be a small parameter. And we have a state space R d plus 1. And we consider the first coordinate separately because this first coordinate will be defined the location of this hyperplane. It will be the x-axis, and the hyperplane will be defined by the point a k epsilon on this x-axis. We will suppose that the family of this point has no accumulation point. And so we have something like this. We have oh, something also. We have x-axis. We have this point ak plus 1, and so on. And here we will have the interfaces, the hyperplanes in the two-dimensional case and the hyperplanes in multi-dimensional case also. So, well, then I intend to consider the system of stochastic differential equation. What we have here? We have an ordinary diffusion, drift vector, and the diffusion coefficient. And I call my process X. X will have now only one. Will be one-dimensional, and Y will be all another coordinate which will tangential on this hyperplane. So normal diffusion plus some additive term. This additive term consists of some coefficient epsilon beta and the local time and each point of AK. Each point in which membrane is, so this hyperplane is situated. As to another coordinate, we have here two coefficients, epsilon beta, theta, and the local time. First of all, some words about what is local time. So here we have symmetric, here we have semi-martingale, continuous semi-martingale, and we define the local time for it as a unique non-decreasing process which satisfies this Tanaka equation, in which we have symmetric signum. And also this local time can be represented by the symmetric formula involving quadratic characteristic of the known process X. What we can say about the solution of this stochastic differential equation? So the process which is the solution of this equation can be regarded as follows. Till the first moment when the X hit one of the point AK, we have an ordinary diffusion. Then when the process reaches one of the membrane, or one of this point, why I say the membrane? Because this coefficient epsilon beta is the coefficient of permeability. Really, we have that on every hyperplane situated at the point AK, there are a semi-permeable membrane, and the process when it reaches this hyperplane move with the probability 1 plus epsilon beta divided by 2 to the positive direction, and with probability 1 minus epsilon beta divided by 2 in the negative direction. Besides, this movement is not to the normal direction, but the process undergoes the oblique reflection on this hyperplane, and the direction of reflection defined by the vector 1 and theta, where theta is the n-dimensional vector which defines the direction of reflection of the process. So we have the process with oblique reflection on this hyperplane. As I explain later, the first thing that it's not clear, it's not very easy to understand if this stochastic differential equation has a unique solution, it's not clear, it's not very obvious, and it's not easy question. So the first question is if at least exists the weak solution of this equation, and is this unique solution? And the other question, if so, this is a question about the limit behavior. So if epsilon tends to 0, what we have as a limit of this process? So this limit we call the homogenization limit, and we want to obtain the limit process for this stochastic differential equation. My assumption for today's talk will be as follows. I suppose that all the coefficients are C2 bounded, and that the point is the family of point AK defined by the following integral, where the function rho is bounded from above and from below, and the matrix, diffusion matrix, is non-degenerate. And now I can say some words about homogenization, mathematical homogenization. So the homogenization of this type. At all, the results for diffusion with membrane, homogenization of the process, of the diffusion process with membrane are rather sparse. It can be mentioned the work by Van Riep, in which she considered the homogenization of planar diffusion with permeable membrane on lines or circles. And as I've already said, the existence is not very simple question, so she just assumed that there exists a unique solution to the corresponding martingale problem. There are a series of work by Hayer and Manson in which they studied periodic diffusion homogenization with one interface, and it was be noted the work by Mahno and his students, in which they studied the one-dimensional diffusion with interfaces. And we intend to consider today the multi-dimensional case. And of course, in one-dimensional situation, we have no obliqueness. So its situation is it is easier not only because of the dimension, but also because of the behavior on this membrane, this interface. So I want to formulate my main result for today. The fourth result about the existence and uniqueness. So under the assumption A and epsilon small enough, the system one of the stochastic differential equation has a unique weak solution, and this solution is a strong Markov process. I'd like to say that the assumption about small epsilon is essential from the different point of view. First of all, the value 1/2 plus 1/2 epsilon beta is the coefficient of penetration of probability. And it is well known from the work of Harris and Sheff, for example, even in one-dimensional case, in very simple case of Wiener process, if this coefficient is greater than 0, there is no solution of such equations. So the first thing that we need small epsilon such that epsilon beta will be less than 1. And another thing that we need, our method is to make this, to consider one membrane and very thin stripe around one membrane. And really, we consider very small epsilon. It helps us to obtain the uniqueness of the problem. And I don't know the method to obtain the uniqueness for all the plane or all the space simultaneously. So epsilon, we need epsilon to prove the existence of uniqueness of the solution to equations. The whole solution will be then obtained by gluing together the solution in small strips. I start with the existence and uniqueness, and I like make some small historical overview. So the first result was obtained by Harrison and Shep, well-known result about the existence and uniqueness, a strong solution of equation with Wiener process and with skew reflection, partial reflection at 0. And the method of Harrison-Shep was as follows. She used this skew function to eliminate the local time and to obtain the equation without local time, maybe with non-continuous coefficient, but without local time, and that was their method. This method was generalized by Legal to one-dimensional, general one-dimensional diffusion with local time, and he again makes some transformation which transforms the initial equation to the new one with discontinuous coefficient, but without local time, and proves the existence and uniqueness for this new equation, and in such way obtains the uniqueness and existence result for the initial equation. The general theory of this kind was outlined in the work of Engelbert and Schmidt. In higher dimensions, the situation is rather more complicated, and in general case, when the coefficients are non-constant, there is not a general result at all. The easier case is the case of just reflection, and this situation is normally considered as a martingale problem, for example, in classical work of Struck and Borodan, or as a Scarofot problem. Here I can mention also the work of Zaitseva, who considered multidimensional Brownian motion with oblique skewness. But I want to emphasize that if you have the constant coefficient, then we initially not have the normal stochastic differential equation system. We usually can solve the one equation and then substitute this solution to another one. So the constant coefficient give us more freedom, and this case is much more easier. In general case, the question about existence and uniqueness is still open. The most strong result was obtained by Nikolai Ivanovich Portenko, who formulated the problem of existence and uniqueness in terms of parabolic conjugation boundary problem. With the help of potential theory method, he proved that the solution of such problem defines the semigroup of operators that correspond to a process with diffusion characteristic exist in the sense of generalized function. And then, together with Kopytka, he obtained the same result for a diffusion with the semipermeable membrane or hyperplane with oblique reflection. But unfortunately, it doesn't follow immediately from this work that the constructed process is the unique solution of a stochastic differential equation with local time. And even if this result can be obtained in technique, how it was proved in one of the work by Mykola Ivanovich, there is no exact result about the uniqueness result, about the uniqueness of the solution to this stochastic differential equation. And we need, of course, this result about the uniqueness, because we need a strong Markov property to gluing together our process. So, and the main result about limit process is the follows. Again, let's assumption are false. Then there exists a weak limit of the pair of process x epsilon and y epsilon. And this process is the unique weak solution of the following stochastic differential equation. Look at this equation. This equation has no local time term more, but instead the system has an additional term in the drift. So here we have an additional term in the drift for x and for y. As to term with a local time, it can be intuitively understandable that if we have previously the penetration coefficient like 1/2 plus or minus 1/2 epsilon beta, if epsilon tends to 0, this member epsilon beta is very small. Yes, so this together tends to 1/2, and that is the penetration coefficient is equal to 1/2. Does it mean that there is no more membrane? But it's interesting that this membrane calculated to make a new member in the drift. And the presence of such membrane can totally alter the initial behavior of the process. Let's consider an example. Let's n equal to 1, so we have now just two-dimensional process. And let this process was very simple, so it will be Wiener process with a drift. The drift will be equal to minus yx. So it can be regarded as the velocity of charged particle in the constant magnetic field and external stochastic electric field in the presence of external stochastic electric field, which is defined by the Wiener process. Let's add membrane to this model. Let membrane will locate it equidistantly at each point epsilon, 2 epsilon, 3 epsilon, and so on. This means that the function which defines the membrane is equal now to 1. The integrated function is equal to 1. And let's define in some large ball around the origin the function beta and theta as follows. So for every membrane now this function are constant, but no, for every membrane not constant because it depends on x. And we have membrane in each point epsilon, 2 epsilon, 3 epsilon, and so on. Let's now make this. Let's now write the boundary process, the limit process, and it occurs that it has f epsilon tends to 0. It has the following form. So we have, according to theorem 2, it has the following form. So we have new term in the drift, and so in the large ball around the origin, the new drift approximately equals to y minus x, and the initial one was equal to minus yx. So we have the rotation direction, alter rotation direction after this homogenization. Let's look at the picture. For example, if we start from the point 2, 2, for the initial process, the drift minus yx give us the rotation in anti-clockwise direction here. And then after the limiting process, the homogenized process, starting from the same point 2, 2, has the clockwise direction here. So this membrane can completely.
And excuse me, where is on this picture places of membranes on the left picture?
There is no places of membrane here
because this is a limit. But
yes, and membrane situated
before the limit. Yes,
yeah.
Where is it?
They were at the point and every point which is in the point 0, epsilon, 2 epsilon, 3 epsilon, minus epsilon, minus 2 epsilon, equidistantly.
Okay, I see. Okay.
Just a moment. Again, problem with so what is and I begin to prove, to say some words about the proof of this theorem and try to explain the main idea. For the first theorem for the existence and uniqueness, the idea is based on the first idea. It's all is the decompose the process into segments which live between the membrane and the reaching of the process by the neighborhood membrane. So if you have, we start, for example, at the point, I don't know, at the membrane which is situated at 0, yes, we consider the part of the process until it reaches this membrane or another one. And to prove the existence of uniqueness, we follow the spirit of Legal. So we want to find some mapping which lead our initial process to the new one without local time. So we transform this transformation we will call by UV. Yes, and then we will see. We use some theorem to prove. We will see the equivalence of these two equation and prove the existence and uniqueness theorem for the new one without local time, and obtain thus the existence and uniqueness theorem for the initial process also. So we will consider the neighborhood of the membrane which is situated at 0 for the definiteness. Yeah, so now beta is defined, beta and theta depends only on the second coordinate of the on the y, and doesn't depend on x because x is equal to 0 now. We defined the function b capital as follows. Look at this function at the first glance. It's if epsilon is very small, so this beta is close to 1. Yes, as close as we want for small enough epsilon. And we define the transformation on the first coordinate as follows. It will be pathwise linear. For the negative x, it will be just the function x, and for the positive x, it will be just the function x b, and b is close to 1, as you remember. And the another coordinate will be the function y minus x theta. All this transformation, generally speaking, is not obviously one-to-one projection on RT plus 1. However, we can prove that this will be projection in a thin strip around the x equal to 1. So thin strip minus n epsilon a epsilon multiplied by RD. Really, the statement is as follows. So this transformation.
So maybe this is the second place where you need small enough epsilon.
Yes, and I tried to solve this. Yes, that I need this for the unique. Okay. Yes. So we can continue this mapping at J to all the space RD plus 1, such that it will be C2 diffeomorphism on each of the half space x less than 0 and x greater than 0, and it will map the thin strip into a little bit disturbed strip in the new space. To prove this, we use the theorem of Adaman. So we need to prove that at 0 the mapping is 0, that the Jacobian of the mapping is not 0 at each point, and this inequality holds. And the proof is not. It can be written almost explicitly, but I use here the function, exactly the function, not the prolonged function. So we need somehow to make it maybe linear in another point, not the 0 a epsilon, but it's clear, and we are interested in 0 a epsilon. So look at this Jacobian matrix. Because x is small, x from this 0 a epsilon, and b is close to 0, this matrix is very close to the matrix of this type. And of course, the Jacobian of this matrix and the inverse matrix will be good, will be close to 1. So not this matrix, but our matrix will be close to 1. So the first condition is okay. So we have the Jacobian, which is not equal to 0 because it will be continuous, because all the functions are continuous here. Then we can consider in the same way the left part of this strip, and even easier because there we have just the function where u is equal to just x. Yes. And then we can see that this function has the limit 0 at 0. So, and it easier can be checked that this condition is fulfilled. And we have at 0, 0. So all the conditions of Hadamard's theorem are fulfilled. And we have that this will be in every semi-space x minus x less than 0 and x plus than 0. C2 diffeomorphism, and at 0 we have homeomorphism, and at all the function, the mapping will be homeomorphism. Then we can let me mention again that the new coordinates are u and v, and we have also the reverse mapping, which we will call the phi and psi. Using the eta formula, we can prove the following statement. Then our initial process is a weak solution of the initial stochastic differential equation if and only if the new process, which we obtained using this mapping, is a weak solution of this following equation. As you can see, this equation have no local time, but rather complicated coefficient. But it occurs that in this coefficient, only the one member for diffusion. So B0, this is the initial coefficient, really B0, and sigma 0 is important. And for another coordinate, just BE minus theta E B is important. Because other one, like psi here and phi here, is small enough and satisfies. It can be represented. It satisfies the following inequality. So for small enough x, and we now have small enough x, it's the small members. And again, we can apply the formula in the proven, as it was proved by Peshkir, for example, with local time to obtain the initial equation. So we have the correspondence between the initial equation and the new one, and so we just need to prove the existence and uniqueness of the solution for the new equation to obtain the existence and uniqueness for the initial equation. And existence and uniqueness for the new equation follow from results by Gao. So we need, namely, it's formulated as follows. If we have a bounded and smooth drift in every semi-axis, u is less than 0 and u is greater than 0, and have discontinuity on u is equal to 0, and diffusion matrix is non-generates, this is the condition of the theorem by Gao, which gives us the existence and uniqueness of the weak solution. And the global solution we can obtain gluing together the solution in each this small strip. And of course, from uniqueness, we have the strong Markovity of the solution. Let me now recall this theorem too. So we want to prove the existence and the existence of limit process for the initial one. This process with new term in the drift and without local time. I'd like to explain the idea first of all. The dynamics of this diffusion with local time is mainly coached by the embedded Markov chain, which implies only the value of this diffusion process is on the next membrane, every time on the next membrane. So if tau epsilon is the first time reaching the next membrane, we are interested in the characteristic operator of this embedding Markov chain. Yes, and it's occur this operator can be represented using the eta formula as follows. So we want to study the dynamic of this pseudo characteristic operator of the embedding chain. So we need to know the behavior of all these members. We will see then that this pseudo characteristic operator tends to the operator which the process we are interested in. Not C, but if epsilon tends to 0, yes. And to obtain the behavior and the estimates of moments for in this Taylor expansion, we use not the initial process, but the new process without local time. And besides, we will see that this new diffusion can be represented as a diffusion with frozen coefficient plus something small. And this helps us essentially to obtain this asymptotic.
So you prove the convergence of the characteristic operators in some space or not?
No, I
get an idea how it looks like, and then work with diffusion processes.
I prove the main result in as we prove in normal sense. We prove the convergence of distributions, and I prove the compactness. So it will be the main idea is trivial, but we need more technical. We need to have more. Many technical results. Yes. To obtain then the just formal way. And
but if you have convergence in some sense of generators, maybe you can apply some results about the compactness of Markov process, for example, from Azer and Kurtz. Yeah.
But the first question, how we can guess the limit operator, yes?
But you already have an idea. You get it already, yes?
Yes. So let me explain, okay?
Okay.
So that was I said that the generator of the limit process will be the point-was limit of the sequence of epsilon, and we use the standard step of establishing a weak relative compactness of the family, and then we use the martingale formulation to prove that the limit process is to prove the limit of finite dimension, or not finite dimensional distribution. So first of all, we know, let us consider again the process in the neighborhood of 0, and we will study the first time when x exits from the interval minus rho minus rho plus, for example. This will be the distance between, it will be the next point, AK and AK plus 1, yeah? And we note that from the left side, the new process U has the same point minus rho, and from the right side, it has the same point, but a little bit distorted from the initial process. Then for new process using the Lyapunov function, we obtained this estimation for the first exit time for the new process, and then prove that it is almost the same as almost the same as the exit time for the initial process.
Excuse me, as I see you get the moments with this epsilon. Yes,
Yeah.
so
Yes.
it is interesting, and it means that which kind of Lyapunov function do you use?
I use a Lyapunov function with this exponent, and then let me just a moment. It will be with this. It will be this exponent and multiplied by alpha epsilon square minus x square, I think.
So it looks like minus parabola and something, yeah?
Yes, minus parabola and something, you're right.
Mm-hmm. Mm-hmm. Okay.
Yes,
so,
and
because it is interesting that usually we get some estimation like this for usual diffusion process. We use this parabola at least, and maybe it's. I just want to get the flavor of this at least phase transformation, which kill local time, where it has its influences here in this statement, or this statement does not depend on the.
Yes, of course, we use the new process in the proof, because we apply this Lyapunov function not for initial process, but as you said, for normal diffusion, which is the new process, transformed process. So really, yes, it's as usual.
So you get this epsilon minus 2 from this phase transformation, yeah?
Yes, yes.
Okay, thank you.
Okay. And also we have the estimation for all the coordinates except x with in this scene strip, yes, that y is not go very far from the initial point also. Well, this about the new process. It occurs the new process can be represented, can be expanded in Taylor series, yes, and then representing in the following form. It will be the sum of the first member, which is just diffusion with constant coefficient, with frozen coefficient. That was what I said. Yes, and just linear drift. So very simple one. And then we have martingale, and we have an additional term. And intuitively, we have here x again and y minus initial point again. And we already know that x is small and this difference is also small. And about phi, I've already said that this is small member. So, and not intuitively, but formally, we have the next proposition that that A and M will be very small. So as epsilon less than epsilon in power 3 and 2 respectively. And in this way, the behavior of the process X, of initial process X, will be defined as, by the behavior of the new process R. But the exit time of the process X will be coincide with the exit time of the new process R, which you remember has the frozen coefficient, good frozen coefficient. It's just a Wiener process with plus some good drift. Yes, and so to obtain the sum for exit time for X from this strip, we use this well-known formula for the normal Wiener process, normal diffusion, yes, with Wiener process with some not Wiener but normal process, okay, Gaussian process with constant expectation and constant parameters, and we obtain here here first time we have something like our answer. Yes, just we have here expectation B rho and divided by the first row of the diffusion matrix. So this will be result for X, which is follows from R, because other coefficients are small enough. We have the first exit time for X, we have the probability of exit through the left and right hand. And we have the second moment, and we have the expectation of the time, of the exit time. This is just a technical, so we can prove that it's almost the same time of the exit for R and for the process X. So now to the main theorem. We need to prove weak relative compactness, and we need the convergence of finite dimensional distributions. I recall here again that I omit the part with technical estimation for example, difference y minus the members of the Taylor expansion, because they are used here essentially. So we relatively the main result which we will use here is the follows. Let's consider the number of visiting the different membranes till the time 2 by the process, and denoted by new t. Okay, then we have the following result, that this new for the time lambda is greater than k, where k is constant, some constant, lambda is now time, and epsilon square, this is epsilon square. This will use essentially in the following proof, this statement. So we prove the weak relatively compactness in the Skorokhod space D, not in C, and use as usual component containment condition and I'll do criterion. To prove this, we use this lemma I just show you. And this is the statements themselves. And the convergence of final dimensional distribution, we will prove using the martingale formulations, and it will be follows essentially from the next lemma. And the lemma is as follows: that this difference, yes, is bounded from below, from above this pseudo generator of this embedded Markov chain, plus something under the integral. And how we prove it? We consider again this expansion in Taylor's theory, and previously we obtained the estimation for each member for all these difference using the new process, the dynamic of the new process, not the old one with the local time. And it occurs that they give together this pseudo generator itself plus something small. So this give us this convergence of the distribution. So I even was faster than I was going to be, but I'd like to stop here.
Okay, thank you very much. Maybe somebody have comments or questions, please. Okay.
Just maybe one small question. So I'm not very familiar with this kind of homogenization result, but usually in stochastic homogenization, the parameter epsilon itself is random. How is it that in this case, to create a weak solution, you've defined, you've been able to prove one for a uniform estimate? I don't know if my question is clear.
Yes, thank you for your question. I hope that this is just the first result in this direction. We have many interesting questions then, because this is the first type of membrane. We can there are membranes with a sticky point and maybe with random epsilon and so on and so forth. So we are going to proceed with this result. So thank you very much, and maybe it will be the next one.
So maybe you will suppose that epsilon, if it is random field, some sense like is in the theory of homogenization. So you will suppose that it is independent, maybe from.
Yeah, let's.
Okay.
Just a moment, I'd like to show if I. Just a moment, it will be faster. I want to show you. So for now, I can say the following thing. Here, no, not here. Just, where is my main result? Yeah, here in this new item in the drift, we have beta divided by rho. So they must be somehow the same power of growth of epsilon, because in other situation there will be no this additional member, or we have some explosion or something like this. So this regulates somehow how what we can do with epsilon, and how we can arrange this randomness or not randomness of epsilon. So it's interesting, yes. I must think about it, I think so.
Thank you.
Okay.
Maybe I may make a few comments that it is easier to prove with this martingale type problem than to prove convergence of generators, because when you apply results about generators from, say, ATA chords, you have to think about domains of definition.
Some core for operation.
Yeah, core and core for if you have a process with a local time, it's completely difficult to characterize.
Yes, but those levels look promising because you have this O small from third moment for all functions like C3, as I remember. It's a huge set of functions, so maybe it will be enough. Yeah.
When you study a process with a membrane, then the domain of L is not C3. it doesn't.
Yeah.
You must have some conjugate boundary conditions.
Yes, I understand, but you already made this substitution.
Yeah, but
and yes, and what about the limit process? It can have the maybe normal family of this function f. So it's not clear really which family of function should we consider and how we can obtain.
I agree that I have not proposed full proof, but at least it will be interesting to look at, because actually this was my comment, which I was going to say, that there is a completely deterministic approach. You mentioned this. I think this book, Olenik, Zhikov, and Kozlov. And as far as I remember, they considered some behavior of parabolic equation and generator related to this parabolic equation on some, again, family of functions, and solve this problem using purely functional method, especially when this free term. Now you have a special kind of free term with delta functions, when this free potential has some averaging properties. So at least it will be interesting to look at those theory in this direction and get the generalization, because formulation for parabolic problem when we have a lot of membrane, as far as I remember, Borodin did, so like in 1995. And even I think he said at those times that he wanted to study exactly deterministic problem related to this thing. So why not to look at least? This is my first comment, and another comment is just rather historical. When you say reference about Petchker, I definitely know that there is article of Hans Former, maybe like again in the middle of 90s, where he applied Ito formula to convex function. Yeah? So he definitely have this local time for semi-permeable. This is just historical comment, and it will be useful to look at.
Andrei Anatolyevich, probably Pesker did multidimensional.
Yeah.
It is very routine, how to say, job to write precisely the form of derivatives and how to delete this local time and so on and so forth.
I understand, but as far as I understand, you need only one-dimensional.
No,
when you
no.
The process is multidimensional.
The problem is that coefficients are not constant. You cannot use only one dimension.
Oblique reflection, yeah.
Yes, oblique reflection, and all the coefficients depend both on x and y. So, and this preserves this. We preserve this dependence.
Okay.
Well, the proof is not so difficult, but yes, the proof is not so difficult, but we have to make a reference. Well, I also have one remark about historical. The reference to Professor Portenko's book 1990 is for English version, and for Ukrainian is 1978, and the first maybe paper 1976. So it was before Harrison and Shep.
Okay, thank you. Maybe some other questions, please.
Maybe another stupid question, perhaps. So where I'm from, there is a bit of an industry in physics for deriving effective equations for large systems. So, for example, you have a system of bosons and you derive the nonlinear Schrodinger equation or something like this. I've only now wondered whether such techniques have ever been thought to be applied to these kinds of problems. I don't know if anyone has ever heard of this area, or so like the BBGKY hierarchy in physics, where essentially you have this system of particles with a horrible evolution equation, and you're looking for an effective equation, and essentially the averaging techniques are similar to what is being done here with the homogenization. I don't know if this has ever been.
I don't know the answer, because really I don't know familiar very well with this system. Maybe my co-author.
No, I don't know too.
Okay, thank you. That's something I'll have to look into myself then, but thank you.
Okay, another questions, please. Okay, if there are no questions, thank you again. And I think the next speaker will be Vitaly Konarovsky, yes?
Yes.
Okay, so today we finish our work. See you next week. Bye.
Bye. And thank you for attention.
Bye.
Bye.